Hi madam, I'm Lim Bing Sheng. I'm going to present AFM, which is Atomic Force Microscope. The objective is to obtain 3D surface topography of materials at nanometer to atomic scale. And second, to measure surface forces, mechanical, electrical, and magnetic properties with combined with the sample surface topography. This is the component diagram of the AFM. The first component is cantilever and tips. It used to sense surface force. The second component is laser source. It used to reflect off the cantilever for the photodiode detector to detect the laser. For the piezoelectric scanner, it used to control XYZ motion of the sample. And then sample stage used to hold the specimen, and then computer or controller used for data acquisition and image display, and then active damping stage to isolate system from vibration, because this AFM is very sensitive to vibration. Here's some parameters. First, the tip radius is 5 to 20 nanometer, and then cantilever K constant 0.01 to 40 Newton per meter. Then it's for working principle of instrument. There is two scanning paths. One is raster path and one is zigzag path. The raster path is scanning through the x-axis, going forward and going backward, and then move the y-axis to another row, and then repeat the same process. And for the zigzag path, the y-axis will move constantly, while the x-axis will move forward until the end, and then move backward back to the starting point. The tips is fixed, while the moving part is the sample only. Here is the piezoelectric scanner, and why we use piezoelectric is because the piezo material is controlled by a voltage, and then it will move a very small distance with a large applied voltage. Piezoelectric scanner movement resolution is typically lesser than 0.1 nanometer. It is also an important parameter to the resolution of the result. This diagram shows how the AFM detects the topography. And here's an important point, which the z-axis of scanner will move if detected to maintain a constant cantilever force contact to the sample. First, we don't want to destroy the sample, so we reduce the force exerted to the sample when scanning by moving the z-axis of the scanner downward if the topography is upward. So when the laser detected going down, for here means it detected a higher topography, and then the z-axis will move down. So the photodiode detections is like a pulse. So the result is the combine of the photodiode detector and the z-axis movement. Here's for the physics working principle. Why it causes atomic force? Because it interacting with atomic forces. For example, like van der Waals forces, electrostatic forces, and chemical bonding forces. Because the tip is very small until it can detect some atomic forces. So from 1000 nanometer to 100 nanometer, we can detect electrostatic force. From 100 to 10, we can detect magnetic force. And from 10 to 1, we can detect van der Waals force. From 1 to 0.1, we detect chemical force and exchange force, and 0.01 repulsive force. This is the famous van der Waals force graph, which is plotted from this Lennard-Jones formula. And from the right part, when two atoms are apart, their force is very small. Their attractive force is very small. When they are attracted together, another force coming, which is a repulsion force. And when the atom is overlapped, the repulsive force is the main force. Here's the example of image of the tips. We can see there's a few atoms only on the tips. For the cantilever, we use Hooke's law because the cantilever acts like a spring. AFM have three modes. First is contact mode, second is stepping mode, and the third one is non-contact mode. The contact mode is the tip is keep contact with the sample, so its draw will damage the sample, and for non-contact mode, it hovers up the sample, so it won't damage the sample. But the result is not so good. And for the tapping mode, it is between the contact mode and non-contact mode. The tapping mode is measured like point by point by oscillating the cantilever at its resonant frequency. This diagram shows up different modes using different forces in the van der Waals force. For the non-contact mode, it uses the attractive force, and for the contact mode, it's using the repulsive force. And for the intermittent contact mode, which is tapping mode, it's using the force between these two modes. For different modes, they have different signal detecting technique and its pros and cons and its suitable sample. For contact mode, it is continuous contact with the surface and its signal is by detection pulse. Its pros is high resolution and fast scanning. Its cons is will damage soft samples and the tips will wear. Its suitable sample is for hard materials like crystals. Tapping mode, the tips will oscillate and taps the surface periodically. Its detecting signal is by detect the amplitude and phase change, and its pros is reduced lateral force and high resolution. Its cons is slower. Its suitable sample is hard materials, for example like polymers. For non-contact mode, the tips will vibrate slightly above surface, which is not contacting. Its detecting technique is amplitude and phase change due to the weak van der Waals force. Its pros is non-destructive and its cons is low resolution in air and sensitive to contaminant. Its suitable sample is soft materials, for example like biological samples. So in this diagram, here shows how the phase and amplitude detection of the AFM. When the topography change, it will introduce a phase lag, and for the amplitude, it will shows a pulse, whether down or up. For the phase, it will always shows the phase lagging. So for this, the middle one it is for detecting how hard the surface is. Because the amplitude change in the middle getting smaller means it is a soft surface in the middle. Here's another picture showing that phase detection is having higher resolution than just amplitude. This diagram shows force modulation microscopy, which is how it detects the material is soft or hard. When the material is soft, the force reflected is more softer, means the amplitude will be lower. When the material is hard, the force reflected will be higher, so the amplitude detected is higher. While this diagram shows how topography plus electrical properties can combine together. We can combine it by adding for example like m meter over the cantilever and the ground. So at the same time it detects the topography, it also detects the electrical properties of the material. So this is the journal paper I found from the internet, and this showing that atoms of different materials will have different topography height and also different attractive force, so that we can differentiate different materials by using this AFM. This paper studying alloy materials which have silicon, tin and lead atoms mixed on a silicon 111 substrate. This 111 is a Christology plane. The AFM mode used is dynamic force microscopy (DFM) with frequency modulation detection, a form of non-contact AFM. Cantilever vibrates at resonant frequency. Shift in frequency is measured to detect forces. Force spectroscopy, frequency change versus tip sample distance gives total interaction force. Then short-range chemical forces are extracted. For journal paper 2, it is talking about the electrical property of two different materials. They get differentiated by AFM and STM. The material used is silicon on silver 111. The method used is atomic scale imaging, scanning tunneling microscopy (STM) measures tunneling current to produce high-resolution images, reveals atomic positions, showing silicon's honeycomb structure, electronic structure sensitivity, sensitive to local electronic states, can verify metallicity and detect Dirac Freeman behavior. Layer identification distinguishes first and second silicon layers via periodic patterns and apparent heights. Second layer 3x3 reconstruction shows different patterns depending on tip apex termination. So this is the reference for the paper 1 and paper 2. So what is the source used by AFM? It is laser. And second, result is in 2D or 3D. The answer is 3D. And does it need vacuum condition? FM can work in air, liquid, or vacuum, unlike TEM or SEM. What is the mean roughness and IMF roughness? So average roughness means it takes every point of height minus with the mean of the height and then add them all together and divided by the number of the point taken. And for the RMS, it is taking the every point minus by the mean and then square and then divided by how much point taken and then square root it. That's all from me. Thank you, doctor.